Hi everyone. I'm very happy to be here in a slightly mixed crowd, or at least from my point of view, is not the usual suspects. So I'm excited to give the talk in the first day and be over it and maybe chat with you about various things. Maybe just a explanation about the affiliation. So Aalto University is the Helsinki University of Technology. If you didn't know, they just changed the name. So I'm primarily based there in Helsinki, but also sometimes you may find me in Bonn. And I wanted to report on some old work because the crowd is so mixed, and some more recent work. So the old work is with Ilin, who's somewhere here possibly, and who can sleep in the first half. And the new work is with Sid, who's my grad student in Bonn. Okay. And so I'm coming more from maybe math physics side. And I think physics was mentioned in the somewhere in the description of this conference. So I'm pointing out some kind of maybe physics perspective of things as well. And I hope you will enjoy some aspects of this. Let's see. Oh, this is very fancy. So what am I talking about? I'm talking about some kind of canonical models for curves in 2D that was motivated from physics, from statistical physics, models like pictures over here. So you can take some lattice, let's say the hexagonal lattice over here. You can do a critical percolation there, which means that you just color each hexagon with one of two colors independently at random, and maybe with probability 1/2, so that you get to this so-called critical phase. And then you see clusters formed by, one of the colors if you focus on, let's say, the yellow. Right? And then you might be interested if the system volume stays the same, but the size grows in the sense that you take finer hexagonal grid on this triangle. What do these cluster boundaries look like? So they are curves in the plane in this picture, right? A couple of other examples are depicted there. Maybe it's not so important to describe them in detail, but this one is the so-called uniform spanning tree model on the square lattice. So you see one branch of the tree highlighted. So you uniformly sample a spanning tree that is acyclic subgraph of your whole graph that comprises all vertices. So there are finitely many of them in each finite system. So you can sample uniformly, you can look at this random set, and you can look at paths there. And the last picture is the critical easing model that you may or may not heard about. So there you have two colors which represent two spins. And you see kind of fractal looking shapes there. So this was a motivation maybe 25 years ago, so at the turn of the millennium, by Orel Schramm, who wanted to understand the so-called scaling limits of these pictures. Scaling limit means keep the volume fixed, take the graph finer and finer, and then in the limit you should get some continuum objects. And of course, the tiny loops here will disappear, but maybe some macroscopic interfaces will survive. You can constrain the model so that there will be for sure some interface surviving, like maybe in the middle point. If you make a constraint that the path starting from here, which is actually one lattice step away from boundary, in the tree, there's a unique path branch that's going to connect back to the boundary. When I assume the boundary is part of the tree, I collapse it to one vertex. So I can condition it exit there, for example, and then I will always have this kind of path in any scale. So, and I can ask about what is the limit of this path. Okay, if it was too quick, don't worry. The point is that you can make sensible questions about these models, and you can ask what kind of objects you get in the limit. And I skipped actually the original motivation of Lerner theory because I'm assuming some of you know it. And if you don't really have to. So Lerner, more than 100 years ago, was looking at dynamics of growing domains in the plane, slit domains or more complicated shapes. And you can think about these kind of pictures in terms of growth of this kind of path as well. So then what Schramm was thinking of was that let's combine this theory from classical complex analysis to some randomness. So these models are random. And let's try and describe these limit objects of these models using Leibniz theory. And the input he proposed was Brownian motion. This is a complicated pointer. To drive the learner process.
You can point also at the screen if it's easier.
Yeah, I should. Works there. Okay. Yeah, I was seeing why Alan was standing there because it's a bit complicated. Okay, so that was the motivation. Something you could also use this for was some classical questions about fractal dimensions of planar sets. So there has been a success story of these kind of objects. So this is supposed to be a maybe historical slide, not very long ago, but anyways, here are listed some key results that were enabled by the introduction of this kind of evolution process. And of course, I didn't tell you what the evolution process is yet. I was just showing you some pictures. And the claim is that there is a Leibniz evolution with random input that has been very useful to describe these models. But not only is useful for this purpose, but it's been very rich in various other questions in complex analysis. And it has connections to many areas, actually. So that's why I wanted to start with this. So it's kind of a canonical model of a random path in the plane. Why canonical? So it has some conformal invariance properties that are built into these models because I was using the keyword critical. So if you come from physics side, you know that critical models should become scale invariant in the limit and moreover conformally invariant. If you're not from physics, if you're from probability, maybe you know that standard Brownian motion, the little b over there, that has a certain scaling property. And that scaling property translates to some scale invariance of the evolution process. Other than that, you can just believe me that conformal invariant objects are interesting. Okay. So what is it? So before going to something that I was doing, let me just quickly tell you what this object is because I don't assume everyone knows. So if you know it, you can sleep for a little bit and then hopefully you will come back soon. So these are two simulations of the critical easing model. And you see some macroscopic fractal looking paths there. And the question is how to describe them. Okay. And the object that was useful to describe them, it's called from Leibniz evolution, like was already kind of mentioned. We use the acronym SLE for it. There's a parameter that describes the fractality of these curves. So you see here the curve with different parameters. So when the parameter grows, it's describing the speed of the Brownian motion that is somehow driving this evolution. So here you see the speed is higher in this picture than there. If the speed goes to 0, this curve will look like almost straight. If the speed gets bigger and bigger, the curve starts to make this kind of fjords. So you can describe a plethora of growing curves or maybe growing sets using this description. And here is the recipe. So I was giving you an abstract statement here. I could have given you a differential equation. As I see, today's topic was differential equations, but I don't have any equation in my slides. But there is a differential equation governing this evolution. But maybe you can just look at this picture over here. So because I was assuming I'm in some conformal invariant model, let's say in a simply connected domain, like in the picture over here, and I want to look at an interface between two boundary points. So here is the boundary point, a corner. You see this slightly red highlighted interface is going to go to the other corner in this model, which is an easing model constrained to have that interface. So then I could look at all possible random curves in a simply connected domain, connecting two boundary points, maybe this one and that one. But if I send this rectangle into the half plane that I've kind of done over there, and the end points of the curve to 0 and infinity, I get to the picture over here. And if I assume that the law of the random curve is conformally invariant, I know that if I can describe it in the half plane, then I can push it elsewhere by conform map, right? So it's sufficient to look at the half plane, where things become somehow simpler to describe in detail. Okay, so now I'm imagining I want to grow a random curve in the half plane from 0. So this is the top picture. I don't know if I'm able to use this pointer. Okay, and if I've evolved up to some time t, so I'm gonna call the curve gamma. So what do I know? So if the curve is simple, I could just say that it gives me a slit domain, so the half plane minus the segment. That's a simply connected domain. So I could just unzip it back to the half plane by some well-chosen conformal map, whose time evolution has an equation that I haven't written here. This is found by Charles Loevner in about 100 years ago, or a bit more. Okay, for each time instant, I find a conformal map, right? And then I can follow where the tip of the curve, at the time t, where does it go to? It goes to some point on the real line. That's the boundary of my uniformized domain, right? And I can always invert this map if I found this map, these maps for all time t. And if I know the time evolution of the tip at each time, which is just a random process on the boundary, then I can reconstruct the curve, at least if it was a simple curve. It's of course a bit more complicated otherwise, but let's pretend we are in this simple slit evolution setup for the purposes of this talk, okay? And so either you can try to solve this problem by imposing some constraints and see what kind of conformal maps you can get. That was Loevner's evolution equation. Or you can just axiomatize to say that I wanted to have a couple of properties. One was this conform invariance property in the theorem. And another one is some Markovian property. So because my process is random, I could ask about, does it remember its past? And as I already mentioned, Brownian motion. So Brownian motion is a kind of canonical Markov process, right? In one dimension. And it doesn't remember its past, and it has a nice scaling property. So that led Schramm to guess that maybe this is a reasonable candidate to describe this kind of interface. And indeed, so if you impose the two properties that are stated in the theorem, so conform invariance just means that you can send the law from the half plane elsewhere by conformal maps, and a Markovian property. That means basically what is written, drawn here, kind of, is that you can explore up to some time t. You can look at the future. So what is the future? That's the dashed bit. The law of the dashed bit up there should be the random curve living in the slit domain, right? And growing towards infinity. So that law is the same as the original law from this point to infinity. So there's some kind of description of the time evolution in you can say infinitesimal pieces if you want. And if you look at what it means for this process over here, you see that it must have independent and stationary increments, which is what Brownian motion does. So it somehow really comes from the constraints. The only thing you can have here is the one-dimensional Brownian motion with some speed, which is this kappa parameter. Schramm was using kappa, so we started to use it for eternity, I guess. Some non-negative speed parameter that was in the previous picture. So the speed was kind of telling how the evolution of the tip is moving through the real line. So the speed over here. And then possibly there can be some drift, but my problem here is symmetric, so there's no drift. So upshot, if you impose this couple of natural properties that any physicist would say should canonically hold for these kind of models, you just have a one parameter choice of these evolutions of the tip in this Loevner equation. So that is a canonical description of a random curve in the plane that is conformally invariant. And then you might complain, I'm in a simply connected domain, how about in some other shapes, Riemann surfaces and so on? So you could imagine growing locally in some chart, something like that. It becomes a bit more complicated to describe these curves globally if you're in a more complicated geometry. But in principle, there's an evolution equation that you can just use for short times. So this was really a nice evolution of growing curves.
Sorry, can you remind me, your G sub t, so it's normalized as infinity, is that right?
Yep, so I normalize it so that at infinity's expansion is like the identity plus capacity over Z plus so on. So I have some time parameterization, which is usually done by capacity. You can parameterize in some other ways. And that features in the series expansion of this map at infinity. But of course, if you imagine what it's doing, it's supposed to unzip the initial piece. So it's not supposed to do much at the target point. Yeah, and that's a unique choice of map. Yeah, I'm hiding details in this talk because I was wanting to give you a kind of high level ideas and not destroy everyone yet with formulas. Okay, any more questions or comments? Okay, hopefully it wasn't too boring yet, if you already knew it. So these are nice objects, that's the point. We understand quite a lot because we understand a lot about Brownian motion. But there's this additional complication that these conform maps are rather non-trivial. So then here's a slide about the more general picture, because what I wanted to get to is some geometry underlying these curves, not only fractal geometry, so you can calculate the fractal dimension. It's not the topic of my talk. The topic of my talk is somehow when you shift the randomness away, what remains is the geometry. Of the underlying kind of moduli space or whatever you want to call it. And in order to see that, you actually need to look at more complicated models. So here is the model of several curves. So in the tiny picture here, this is the critical easing model with the constraint that you have alternating spins on the boundary. So here is maybe plus, minus, and so on. And then you see these several curves from different points emerging, right? And they will survive in the limit, and maybe they will look like, so that has more points up there, but anyways, so you will have some collection of curves, and you want the same kind of property that they are conformally invariant. They have some parameter that's related to the fractality, and they should have some Markovian property also in terms of somehow looking at connected components. So, so what is highlighted above is one component in, it's this one, in gray. And I could ask, suppose that we understood this one curve model that was in the previous slide. So how can I understand this multi-curve model in a kind of canonical way with some, symmetry property that is in the box? Is that I could start exploring my picture here. So maybe I discover one of these interfaces, and then I already know where it went. So I can somehow remove that component that I already discovered. I can look at the rest, and that's going to have n minus 1 interfaces if the original one had n. So then I could impose that maybe I discovered everything but one, which is the red one. So the red is unknown. So what is the law of the red one then? It's just the standard one curve model, but in the complement of the other curves, of course, in the connected component where the endpoints are, right? So I decided here how the curves connect for definiteness, but you can do a convex combination if you want to change the endpoint distribution. So in other words, you can somehow discover these models in chunks, and it shouldn't matter which curves you discover first and which one is the last one. So this kind of property should hold for all choices of the red curve, that if I already found all the other ones, so what is the law? The red one is just the usual thing, but in the random domain, that's the gray shaded one, okay? And it seems like an obvious property, right? That this is what should hold. And it was somehow quite difficult to show that this measure even existed and was unique. So that has been a topic of many works. And then you could also ask about what happens in the kappa go to zero limit that I wanted to talk a little bit about, because it depends, it relates to some work of Alex back in the day. So there it becomes also a non-trivial question in enumerative geometry. So first of all, maybe good news is that you can make sense of it. I wrote the formula here, but this only maybe if you already are comfortable with these things, you don't have to remember it. So the box is saying that, yes, this thing makes sense for all reasonable speeds, kappa. If you're an expert, you see I put kappa between 0 and 8, which is the full range of these parameters. And there was a series of different works. Also should probably mention work by Angholden, Sun, and Yu. Also this, I think last fall, constructing these things by conformal welding of some quantum surfaces. So these names are here maybe more from kind of SLE theory point of view. So you can construct these objects and you can show that they are unique. So you can talk about this multi-curve model without ambiguity. The formula here is illustrating how you would try and construct such a measure. And I should have written in the formula that this speed has to be small enough, because you might think about if I go back, so these curves started to look very wiggly if the speed was very high, and then they might start colliding with each other, and this causes some trouble, because somehow in these pictures, what normally happens that they stay separate, or at least if they collide, they don't cross, they just bounce off each other, like there. So if you assume small enough speed, everything is kind of nicer. And then you can say that you just construct the measure of these several curves from the product measure of independent ones, which is down here. This is the caudal SLE measure between the corresponding points and product of, all capital N of the curves. But if you have independent ones, of course, they're going to cross and they are not going to satisfy the symmetry property. So you have to weight this measure if it would be absolutely continuous with respect to the independent ones by some factor that's over here. So that's the Radon-Nikodym derivative. And why did I write it here is that it's a conformally invariant expression involving some parameter, little c of kappa, that is called the central charge, for those of you who already know some connections of these to statistical physics or conformal field theory. So it's a special number. And something conformally invariant, that is the measure of Brownian loops in the domain D. D is my disk here in the picture, touching somehow pairs of the curves. So this is a bit complicated, but it doesn't matter much. The point is that you can cook up some formula of this sort that has been guiding us also to understand the geometry underlying these curves. Because, maybe I can reveal it. So this is to read if you are comfortable with these terms. So the idea is that maybe if I only have two curves, so if I sample one of them, so what is the other one? I need to understand how the law of the other one changed when I changed the domain from the big one. If it was independent, it was just living in the big one, not feeling the other one. I have to understand how is the interaction of that to removing the chunk explored by the other curve. And somehow the interaction is really governed by this kind of measure of loops touching the curves. So here's a picture of something related to the Brownian loop measure. So there's a sigma finite infinite measure on loops on planar domains that gives finite mass to loops that touch two well-separated sets, like in here. So this is a finite number in this kind of picture. And it's conformally invariant because these loops are built from planar Brownian motion. So the upshot is that there is a description, which is reasonably natural, at least if you're in the area. If you're not, maybe you can think about the theorem as an abstract statement that this object exists and is unique. Okay? And it has the nice symmetry property. And what I want to really talk about is to get rid of this randomness and see what happens when the kappa goes to 0. Okay. So let's see. This I already said, I think. So the response of the curve to the change of domain, you can think about it as if you explore by another curve, you delete that chunk, that's changing the original domain. People call it conform restriction property because you make the domain smaller. And you can also think about it as if you would just have a somehow infinitesimal change. So some kind of response of these curves to changes of the complex structure or the metric. So somehow the idea how to construct this thing is really boiling down to how these canonical curves feel the change of the underlying domain or surface. Okay. And this was maybe first implemented by Lolesham and Werner. They have a paper called Conform Restriction. And then there are various other people who worked on this. And I mentioned Loebner energy here because I think it will be mentioned later in the conference. So this is closely related. It's somehow, how to say, some kind of action functional on these curves, which in these particular models you can derive from these restriction properties. And what I wanted to mention before going on is that it's a response of the curve model to the change of the underlying geometry. So this is believed to be somehow a universal property that's characterizing any reasonable curve models. So the last bullet is trying to say that if you have a measure on paths, or you could also think about loops if you want. So in these pictures, they were loops, but I was ignoring them. So what is somehow a canonical description of those? So one was I was claiming from Brownian motion evolution. But if you don't know this dynamical perspective, we try to say that they should satisfy this kind of restriction property. So some given response to the change of the underlying geometry. And it's actually conjectured by Kontsevich in a paper with Zhuhov that very loosely speaking here, because it's a conjecture, is that this kind of restriction property that you can very loosely speaking, write in terms of the response of changing the domain has to do with some conformal invariant quantity times a parameter. So that should characterize uniquely these canonical measures on paths or loops. And actually such measures on loops were relatively recently constructed by Jean. I think the 24 is probably the publication year. So it's already a few years ago. It's called SLE loop measure. So you could think about in terms of these paths that I'm describing, loops inside the domain. But the uniqueness part is still open as long as I know. So therefore, for me and some other people, it has been of interest to understand this response of these curves to the changes of the metric better. Okay. So that's one motivation, at least for me, to see why and how these models should be canonical. So there is a construction of very general measures on loops and paths that satisfy this kind of well-encoded property under changing of the domain, which looks a little bit like that. But it's not known in general whether that's sufficient to uniquely characterize those kinds of measures. Okay, that was a mouthful. But the point is that, at least for the purposes of today, what I wanted to highlight was understand how those curve models really feel the geometry. And that you can see a bit better if you get rid of this randomness in the growth. Okay. So now I switch gears a little bit. So the left picture here, maybe some of you have seen a subset of this. So somehow first half of my talk is old and the second half is new. So maybe something for everyone. So the right-hand side picture has this kind of fractal interfaces from the statistical physics models. that people have been interested in and that are reasonably well understood now. So of course, convergence results are very hard. So this is only known for some subset of cases, but conceptually we understand them very well. So then you could ask, get rid of the fractality to get some nice smooth shapes, which are the green guys here, and look at the asymptotic convergence of these measures on curves. So remember, my curves are random. So what is a random curve? It's a probability measure on curves, right? Then I can look at some concentration of measure phenomenon. So in the picture, the red curves are supposed to be realizations of these random curves. And then I'm asking about the probability of them staying somehow close to some kind of optimal or some given maybe smooth configuration. So this is a large deviation phenomenon that I think it was really initiated by Elin in her thesis, but there was a couple of maybe thoughts before that by some other people. But there has been a great success in the recent few years about this. And here you actually see very interesting connections. So now you can forget about the statistical physics models and too much about Brownian motion. So we talk about measures on curves, which are somehow canonical. And we want to see what happens in this limit. And I have a warm-up slides here just for everyone to understand what the limit is trying to do. It's quite easy to picture, but just to keep it light. So I was encoding the growth of my curve to one-dimensional Brownian motion with some speed. So here is now just the path of one-dimensional Brownian motion. That is supposed to be the evolution of the tip of the curve on the boundary of the domain. And there was this speed, right? And the speed was supposed to go to 0. So I can look at some time window. And what does it mean when the speed goes to 0? Of course, means that my Brownian motion flattens out, right? So it becomes a straight line. But then I can ask how does this phenomenon happen asymptotically? So if I didn't allow it to flatten, if I conditioned on it to be staying close to some other kind of curve, W, which is some given function. I didn't draw it in the picture, but you can imagine some other function, and I could ask if the Brownian path that wants to be very flat, I impose that it should be close to some given other path. So that probability is going to be exponentially small because the Brownian motion really wants to be flat, right? And then you can look at the rate. So there's going to be some rate kappa, or 1 over kappa. Kappa goes to 0. And then some functional I of the W, which is some energy measuring the energy of this kind of given path. So you see, if the W is the constant function 0, I would expect that maybe then this probability is close to 1. So this energy, this I, should be just 0. It's going to be non-negative. The formula is there. So zeros of this energy functional I will be somehow the places where the concentration is happening, because then this exponential is actually just 1, right? Because it's exponential of 0. Otherwise, there's going to be some decay. And you might recognize this is just nothing but the Dirichlet energy of this path, right? So it's a very classical result. So people call it maybe the energy, at least in this business. And then I could ask the same for the curves. So of course you say that, yeah, it should be then trivial, just transformed by the conform maps and so on. But actually there's a lot of technical work to be done to make it precise. But at least you can ask the same question. So now for two-dimensional curves, maybe I have my desired curves there, so the green ones, and I'm asking for the probability of the random curves to stay somehow close to those in some suitable topology. I need to say what being close to means, right? So it's very loose. But nevertheless, in any reasonable sense that this decay phenomenon would work, we can try to figure out what is the this energy functional of these curves from the knowledge of the previous thing. And of course, if there's just one curve, maybe I show it, is the Dirichlet energy of whatever was driving it. So this W was the image of the tip, and eta is the kind of a green curve. Gamma is a random curve. I just wrote SLE. So there's a lot of notation. But the point is that you can, in general, you can write something of this flavor. So we call it still the energy of this curve collection. And I wrote it as something that I call H minus the minimum of H times some constant. So I is the usual letter for energy or some kind of action functional. But what's easier to describe is what I wrote as H, but that's not going to be non-negative. So I have to subtract the minimum and show that the minimum exists. And the H formula is here. So it looks horrible, but it's not that bad. Because what is here? So here is just somehow a kinetic term. So these are just individual energies of the individual curves that we already know from the Brownian motion theory. This is some interaction term that was appearing in the Radon-Nikodym derivative to construct these measures. I will write you a nicer formula very soon, but if you know the Brownian loop measure, this is somehow related to that. And I included a third term that encodes some moduli, that is the endpoints of the curves, but you could just also remove it, because when I subtract the minimum, the last term is independent of the curves, right? So I encode there so that I can write the next formula correctly, okay? But the point is that there's some kind of independent contribution plus interaction, plus maybe some geometric information in this rate function. So we call it rate function or energy. So it's describing the concentration phenomenon, okay? Let's see, so here's another formula that I think is a bit better for most of us. So what changed was that you see some Laplacian operators, some determinants decorated by zeta, because you have to make sense of the determinant in a suitable way in terms of the regularization using the zeta function. It doesn't matter for too much, but I believe some of you are familiar with them. And what do I look at? I compare these determinants in various components of my shape. So the green things here are these curves eta that I'm asking the random curves to be close to, okay? And I'm describing the energy of those curves in terms of this H, which we would call potential. And what do you look at is somehow the determinant of Laplacian in the whole domain without anything compared with the determinants in different components. So you see the jump at each curve somehow. So C is any of the different colored connected component of the complement of these curves. And then there's some constant again, because I didn't want to write something wrong in the slide. But the constant only depends on the number of curves. Okay. It's a little bit complicated looking, but the point is that this energy functional is really governed by somehow the response, not really of the curves to the change of the domain, but now of the domain when you put the curves there. So it's somehow the effect of placing the curves in given positions, and the effect you can measure in various ways. Maybe the easiest to describe is this one. You see how the Laplacian determinant changes if you make this into several components. If you know stuff about the Neumann jump operator, you can write in that way, or in many other ways. All of them look a little bit complicated, but you see that there's some geometry, right? By the way, it's the Dirichlet Laplacian, if you're wondering. So there's some geometry that you see when you turn down the randomness. So in the box, so now the claim is that you can make the box precise. And what happens in the right-hand side, I hopefully defined to you, modulo some regularity assumptions maybe, because you might complain that when is this defined and so on. but let's not worry about it here. And the left-hand side, what does it mean, this probability? You have to be a bit more precise about if you want to rigorously give a statement. But the highlight here was really that in the limit, when you take the randomness away, you see some geometric objects, which actually also very universal. So that is a remarkable feature of these curve models. Okay, so here is the precise statement written. So if you like, you can read what the asymptotic really means here in the two things. I put the exponential, in the log, so it looks like that. And the limit of this probability doesn't usually exist as such. So you have to sandwich it between open and closed sets. So this is the usual formulation of a large deviation principle in probability theory. So if you don't know it, you really don't have to look at these formulas. You can think about the first line. So that's the idea. And then somehow the key maybe technicality here is to describe the topology of the curves. And you can describe it in various ways. I listed a few names, maybe some names are missing. So we were working on this with Eveliina on the Hausdorff distance, which was maybe the easiest distance you can put on curves, because what are they? They're just closed subsets of your domain, right? So you can ask about being close in Hausdorff distance. Yeah, and this is actually ages ago, but the publication year is 24. So anyway, we established this complicated statement in the Hausdorff distance. There's been some students who I wanted to just mention because I think they are very, very good, and hopefully you will meet them in some meetings later. So there's a student Vlad Guskov in KTH of Fredrik Wiklund who was looking at the same thing with parameterized curves. So you can encode time parameterization. That was the dynamical description of the growth. And then the thing becomes harder. And one of my students kind of strengthened his result recently, but it's not on archive yet. So you can try to improve the topology here, and of course various other things. But maybe for the purposes of this talk, what the point was really that there is this concentration phenomenon, so I'm going back, governed by some geometric quantity that we would call Löwner energy. And now, because we have a concentration phenomenon, exponentially fast, we could ask, so is it obvious that there's some unique minimizer of this energy? So remember that the energy functional is non-negative. So this exponential is going to decay very rapidly unless the I of eta, the energy of the collection of eta curves, is 0, right? So then you can ask whether there's a unique configuration or maybe several configurations of curves that have 0 energy, because that's then where this measure is concentrating to, right? So this is another basic question you might ask after or even before you prove this kind of concentration, if you believe it's true. And that's where the fun starts, actually. So now, hopefully some people have energy left for some other things. So I want to go to more geometry, also to something Alex worked on. Hope Alex, I don't see him, but hopefully he's there.
He's there.
This was actually familiar to him, I think. So now a couple of slides is still old stuff, and then maybe quickly I mention some more new stuff. Let's see, I think I included a very horrible slide that maybe I regret now. I wanted to list various pointers that I will not be able to talk about. So you see the first bullet I mentioned. The second bullet will come soon. Then there's various other things, actually some integrable systems, some CFT things, some geometry that I don't know if these will feature later in the conference. And actually some other things that maybe I'm able to mention in the very end. So this, you see all this, most of these years are very recent, except for some very classical things which are from complex analysis. So it's been very much growing these past years. So there's a lot of connections of Löwner energy to various things. And what is Löwner energy was this action functional of these kind of curves. Okay, so the question about minimizers, at least I should mention, because it's kind of, I think it was liked by Alex. So Alex already knows this, but maybe not all of you know. So you can classify the minimizers in this particular setup. And I think we will hear about more complicated setups later in Eileen's talk, I hope. So this is maybe related to that. But here was some kind of connection to algebraic geometry that was quite fun. So here is the kind of key observations. So one is the following. So if you want to minimize this energy, so what does it mean? Minimize actually will be that the energy is zero. So you can look at the formula that was appearing earlier, or you can remember this nice symmetry property of the construction of these measures, which was saying that if I explore n-1 of the curves, what does the remaining curve look like? It's just the one curve model, but in its own component, right? And this is somehow inherited into this limit. So that was the first thing that we were, of course, expecting. So we call it geodesic multichord in the paper. So what does it mean? So the picture is a bit complicated. You can look at the upper half plane. So here are these green curves, if you can see. And one of them is red. So let's say I explore the green curves. I'm asking what is the, now there's no probability measure, but what does the red curve look like? It's going to be a geodesic, but not in the half plane. It's going to be a geodesic in the union of this yellow phase and this purple phase, if I'm at the minimizer. So somehow what happens to the one curve model in this limit is that they become geodesics. You can see it easily for one curve case, because if you just drive your Levin evolution by a constant function, it becomes the straight line from 0 to infinity in the half plane. So that's the hyperbolic geodesic. It's conformally invariant. So somehow this is very natural to expect. So then it only suffices to classify those kind of curve configurations, which sounds like a very reasonable task, but well, it wasn't so easy. So we call them geodesic multichords. And then you can observe something that helps in the classification is that if you do a reflection to be on the Riemann sphere instead, so now I include the lower half plane, and I can just reflect these curves. They became blue, I guess. So I have this kind of graph on the Riemann sphere whose vertices are the endpoints of these original curves that I had, whose edges comprise these edges in the upper half plane, their reflections in the lower half plane, and these line segments on the real line. It's some connected graph. Each vertex has degree 4 on the Riemann sphere. So what does it look like? It looks like a real locus of a rational function. You can make it precise by Schwarz reflection. So you see that there's some bipartite coloring. I forgot to color this here. Sorry about that. So that every other phase of this graph goes under the rational function to the upper half plane. Every other phase goes to the lower half plane. And then you reflect. So you get some covering map of the Riemann sphere by itself with a specific ramification profile at these given points. Okay. So any minimizer of my energy functional gives such a map. I have to fix the points, of course, which I always considered fixed, and how they connected together, which gives me the graph. And the graph gives me a rational function. And then you can actually notice that you can classify those rational functions. So this was the observation we made that relates to the Shapiro conjecture about these rational functions, or actually that their reality in a sense. That was worked on by Alex, and I think Gabrielov is somewhere here. So yes. So that special case of a Shapiro conjecture somehow naturally came up in this problem we were considering. And I summarized it here in a bit convoluted way. So the point is that any minimizer of my energy, there is one by some analysis arguments, and it's unique because the corresponding rational functions in the third bullet are unique. So once you know the classification of the rational functions, you get the classification of these minimizers. So then it's exactly as you expect, in the sense that if you fix your points on the real line, that will be critical points of that rational function, or alternatively endpoints of these curves. There's a Catalan number of different graphs associated to that, that is telling how these points are pairwise connected. And this is what we saw in the curve model, right? So it's really what you expect from the probability side, but to prove it, you get to algebraic geometry. So you can enumerate all the minimizers and they are exactly what you expect, which is, I guess, not the case in more general cases necessarily. So this case was very, very rigid. Okay. And in particular, from the construction, you see that this rational function that you get from this little picture, it's a ratio of real polynomials. So the conjecture, if you're familiar with it, was about each equivalence class of rational functions containing a real representative. So that was somehow a byproduct of what we wanted to see. Okay, I think I'm probably doing quite badly with time. So how much time do I have?
8 minutes.
8 minutes. Oh, okay, that's very generous. So then maybe I can say a few words. Yes, about the second part. First, I thought I will only discuss that, but trying to think about how to make a story out of it needs more than one evening. So then I was lazy and I put the whole story in the front. So this is something I was working on with my student Sid in Bonn, or mostly he's been working on it and I've been just trying to help. So this is pertaining to the models on loops in some very vague sense. So remember that we could have canonical models, hopefully, not only for these paths between points, but to loops and all kinds of shapes. So here is not loop, but here's an annulus. So what is a loop? It's a boundary component of an annulus. And if you remember, I mentioned that these canonical models for curves were supposed to be somehow singled out by some conform restriction property that is describing how they respond to conform a change of metric, the underlying metric, or how do they respond to the change of the domain that they live in. And trying to understand this somehow constraint, because proving the conjecture seems too difficult, I was thinking that let's try to understand the response of these kind of boundary components of annuli or more general shapes if you change the complex structure. And I was a bit surprised that not everything was known, or at least I'm not aware of it being known. So of course you maybe know that if you make a deformation somehow locally, you have to encode it into a vector field. And those vector fields have to do with the width algebra or the Virasoro algebra as appears in conformal field theory. And we wanted to somehow do a computation to see that from this picture. So it's motivated from Segal's axiomatization of conformal field theory, which is that you have all Riemann surfaces with some genera, maybe here's a picture, and you have your theory somehow there and you glue them together to get bigger surfaces, and there are lots of kind of axioms that we don't have to repeat. How this thing should be done and related to this conformal field theory. But from the naive perspective, you could just try to understand how the Virasoro algebra, the conformal deformations somehow appear in this simple looking construction. And so now there's a lot of notation in the slides, but let me highlight just what we wanted to do, and you don't have to worry about the notation. So I'm going to look at genus G Riemann surfaces with some boundary components, number B of boundary components. And I want them to be parametrized, okay? Because then what I want to do is to deform the structure and possibly also the parametrization and see the response to my model to that. And I have to do two things. One is that I could just reparameterize. So let's say a parameterization, what is it? It's a map from the circle to the boundary component with some analyticity properties, because otherwise the computation will not work. So the diff plus n S1 is just the sense preserving diffeomorphisms of the circle that extend to some color neighborhood. Okay, and they sit inside of some space I call def, which is complex deformations. And this is not a group, but you can make sense of it in terms of vector fields. Maybe I reveal. Don't worry about all the text. I was just encoding here in case you know something of this, you can read. So the point is that I cannot describe a group governing actual deformation of the complex structure on the boundary, but I can describe it in some way of flows. And nevertheless, then I kind of use a group notation, this capital def, to denote whatever should be the deformation there. So in principle, you can compose some conform maps together, right? Or holomorphic maps in the common domain of, so if the definition of the next map is inside the image of the previous one, you can compose, right? But you cannot make a group out of them. So the idea is that in a small enough neighborhoods, you can do something. You can look at these deformations, and you need to look at that, not only parametrizations, to see the deformation. So that's the nuisance. Right? So I call it complex deformations. And then
You're not asking for your annulus to have some definite size. So you're allowing for the annulus to be.
no. So I'm asking the annulus to have some boundary component parameterized. And of course, then I know the size, but then I'm going to deform it. And I'm going to ask, how does this deformation show in an algebraic sense somehow? Because I wanted to see the Virasoro algebra. And to get there is very complicated, and I will not be able to do it during the talk. But you have to look at a central extension if you want to see a Virasoro. So we kind of wrote here very complicated words. So for each surface, you can associate the line, which is called the determinant line. And you actually have to look at also how the deformation is acting there to see the Virasoro algebra. And in the end of the day, so that's the parameterization, which was somehow analytic in some neighborhood. So if I deform, it becomes something like that. And then you can try to ask how to see the effect of this to the loops. Okay. And since I have to speed up, let me just say that what you really do is you look at vector fields. So you end up in some analytic vector fields of the circle, complex analytic. You want to central extend in order to see this kind of anomaly that physicists say. So if you want to see the response really to the deformation, you somehow have to see some twist, which is in this short exact sequence. And the claim is, let me show you claim, is that once you calculate everything, you will find a very familiar thing, which is a co-cycle in the Lie algebra, imaginary part of that, which gives rise to the Virasoro. So this is known as Gelfand-Fuchs co-cycle. And you see a lot of notation, but this formula is not too bad. So I look at some two analytic vector fields, which are deforming my parameterization. I look at the effect of that in my model that I haven't described very clearly. But the upshot is that you can do a computation. What you see is C, which is the central charge parameter that appeared previously in the conformal restriction property, 24 pi, imaginary part of something known. And now, because I have to end, I want to show one, sorry. So just details if one wanted to see them. I want to show this slide before ending, because this relates to the energy of the loop. So maybe you can imagine a loop on the Riemann surface. So we don't know what the energy is unless we are on the Riemann sphere, I guess. But if you can cook up a reasonable energy on surfaces, I believe it's the same. So it's on this side. Energy of the, now the gamma is a loop. C over 24. So that thing equals something, which is complicated, but that's what appears in the model of these glued surfaces. So now it's super fast, but in the last formula, you see Laplacian determinants. That was maybe ringing a bell. Here you see something I didn't define to you, okay? But the point is that in the end of the day, you get back to the Löwner energy of the loop in this very geometric way that's motivated by some Segal conformal field theory axioms. Sorry about being so quick, but I don't want to go over time. Happy birthday, Alex.